In this video, we're going to look at a piece of mathematics which has an astounding and beautiful result. It's a piece of maths that's very simple to do, but what it does is it opens up whole new counterintuitive ways of thinking about certain mathematical objects which shatter our sort of common sense beliefs about what these items in maths are. And the piece of maths we're going to be looking at is this. It's the sum of all the positive integers. So it's 1 plus 2 plus 3 plus 4 plus 5 plus so on, all the way to infinity. Now, when we first look at a sum like this, it almost seems trivial to say that, well, obviously, the answer to what that sum equals is infinity, right? But let's just have a think and have a look if we can approach this sum in perhaps a different way. So, this is where we're trying to get to, but before we can approach this sum, we need to do a different sum. And I'll call this other sum A. And what A is equal to is 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on to infinity. I said it was obvious that this top sum equals infinity, but it's very unobvious what this sum should actually equal, right? Because if we were just to take the first term of A, then it's equal to 1. If we were to take the first two terms, it's equal to 0. If we were to take the first three terms, it's equal to 1. 4 terms, 0. So it seems to be oscillating between two values, and it's very hard to say, well, if we take all the infinite terms of this sequence together, what should they equal? But there's a way we can approach this sum, right? And what we can do is we can take A and we can add it to itself. So I'm going to do A plus A, and I'm going to write out the second A beneath it. So the first term is 1, so plus 1, and then minus 1, plus 1, minus 1, plus 1. So this is A plus A. Now we can make an observation, and we can say, for every term in the second A here, 1, I've got a corresponding negative 1 in the first term. So if I group these two together, they equal 0. And I can do this for every single term now coming up in this series. I can pair each one which is negative in the first one with one that's positive in the second one, and I compare each one that's positive in the first one to one that's negative in the second one. So everything here cancels. So we can get rid of that term, and then likewise for the next, and the next, and the next. And we found that even though we started with an infinite sum, by pairing up the terms like this, we've now had it reduced to A plus A equals 1. We've lost the infinite terms, and we've just got a very simple equation that we can solve. So if A plus A equals 1, what does that tell us? That tells us that A is equal to 1/2. Right, so we've made progress, but we're not out of the woods yet. The next sum we have to consider, let's call B. So what B is 1 minus 2 plus 3 minus 4, and that goes on to infinity as well. So you can see we're getting closer to S here, but instead what we have is that every odd term is positive, and we add it, and every even term is negative. So now this is really unobvious what this will equal as we go to infinity, right? But like we did for A, we can add B to itself and see what we get. So B plus B. So I've got my first B here, and just like I did for A, underneath it I'm going to write the second B. So plus 1, minus 2, plus 3, minus 4, and so on. And just like we did for A, we can make an observation at this point, right? We can say, well, if we pair the first term in the second B with the second term in the first B, if we pair those two together, minus 2 plus 1, we have minus 1. And then if we pair the next two terms together, plus 3 minus 2, we get plus 1. And if we pair the next two, we get minus 1 and then plus 1. And a little bit of thinking will convince you that this will happen now for every single term in this infinite series. So what are we left with? Well, b plus b is equal to 1 minus 1 plus 1 minus 1 plus 1, so on, which is equal to a, the first sum we computed at the beginning. So if b plus b is equal to a, well, a is equal to 1/2, so 2b is equal to 1/2, and we end up with b is equal to 1/4. Alright, so we've done a lot of the legwork now, and well done for sticking with it, and we are almost there. The last step we have to do is this. We take s, our sum of natural numbers, and we subtract from it b, the alternating sum of natural numbers which we just calculated. So, let's write this out. We have s equals 1 plus 2 plus 3 plus 4 plus 5, and so on. And then b minus b, remember. So the first term in b was 1, so we're going to do minus 1. The second term in b was minus 2, so we're going to add 2. And then it alternates. So minus 3 plus 4 minus 5, and so on. Now, what are we left with? Well, we can see that every odd term in this sequence is going to cancel each other out. For every 1 we have in s, we're going to have a minus 1 from minus b. So all the odd terms cancel, and all the even terms add up. So what we're going to be left with is, well, nothing from this term. 2 plus 2 is 4. Nothing from this term. 4 plus 4 is 8. Nothing from the 5s. 6 plus 6 will be 12. And so on. And what does this equal? Well, we can take out a factor of 4 here. So if we take out the 4, the first term is 1. 4 goes into 8 twice, so the second term is going to be 2. And then 3. And 4, and hello. What are we left with? Well, this term here, all that is the sequence of positive integers, the sequence of natural numbers. That is exactly this s we started with. So now we have s minus b is just equal to 4 times s. And this is an equation we can solve, right? So let's rub that out. So we've ended up at the situation where we say s minus b is equal to 4s. And a little bit of rearrangement here. We'll take this s over to this side. So we have 3s is equal to minus b. And remember, b was a quarter. So we have 3s is equal to minus a quarter, or s, which is the sum, the infinite sum of positive integers, is equal to minus 1 over 12. It's minus a 12. This is an incredibly counterintuitive result. We've taken the sum of the numbers starting from 1 and only getting bigger, and when we've computed what that should equal, not only have we found a number smaller than even the first term, we found a negative number, and we didn't have a single negative number in this sum. Now, what's more remarkable about this is that not only, I mean, you might be tempted to say that, well, what we've done here is some sort of mathematical trickery. We've manipulated infinite sums in ways which we're not really allowed to do, and so we've arrived at a result which isn't commonsensical. Fair enough. More important than that is that what we find is in theories like quantum mechanics, we have these infinite sums appearing in the equations for the dynamics of systems, right? And what we found is that if you take this infinite sum in your theory and you put in the value minus a 12th, then what that gives is concrete predictions about the real world that are borne out, that we actually see, we can experiment, and we get experimental justification for this. If you were to put infinity in the equations of quantum mechanics when you saw this sum, you would get a system that blows up, that just has no sort of basis in the physical world that we actually see and we actually measure. But if we substitute for this infinite sum the value minus a 12th, then that gives us incredibly precise predictions for the observations which we can make. And so the incredible thing about this piece of mathematics and this sum is not only is it so counterintuitive, not only does it seem to go against all the preconceptions we have about how addition works and how infinity works and how sums work, but it gives us something that is experimentally verified. It not only is this bizarre, but it matches with the world we see around us. And that's why it's such a beautiful piece of mathematics, not only because of the simplicity we get at arriving at this result, and not only because it's so different to the way we normally think about how mathematics can work, but also because it gives us an insight that the rest of the world is equally as counterintuitive and equally as bizarre. Yeah.